All right, let's dive right into one of the biggest, most mind-bending paradoxes in all of physics. It all really boils down to a single, wild question. Seriously, just stop and think about that. Can a decision you make, right here in the present, actually reach back in time and change something that's, well, already in the past? I mean, our common sense just screams, no way, that's impossible. But when we get down into the strange world of quantum mechanics, things get a whole lot weirder.
And look, this isn't just some philosophical thought experiment. We're talking about a real, honest-to-goodness experiment called the delayed choice quantum eraser. And what it reveals about the very nature of reality is, trust me, stranger than you can possibly imagine.
So to really understand that delayed choice part of the name, we first have to get our heads around the basic choice that a quantum particle faces all the time. Is it going to be a particle, or is it going to be a wave?
This all comes from the famous double-slit experiment. Here's the deal. You fire something like a photon, a particle of light, at a barrier with two slits. If you watch to see which slit it goes through, it behaves like a tiny, predictable bullet, a particle. On the screen behind it, you get two distinct bands. But, and this is the crazy part, if you don't watch, it acts like a wave going through both slits at once and creating this complex interference pattern. The key takeaway is this: having that which-way information forces it to act like a particle.
The great physicist Niels Bohr called this the complementarity principle. It's a fundamental rule of the quantum game. An object can show you its particle side, its path, or it can show you its wave side, the interference pattern. But it can't and it won't show you both at the same time. Knowing one completely erases the other.
And this right here is the heart of the puzzle, first posed by the physicist John Archibald Wheeler. What if you let the photon hit the screen, its journey supposedly over, and then decided whether or not to look at the which-way information? Would the pattern that's already on the screen retroactively change to match your choice?
To test this incredible idea, scientists designed an absolutely brilliant setup. It's basically the double-slit experiment, but with a fantastic twist that involves a special crystal and a pair of quantum twins.
So here's how it starts. A photon goes through one of the two slits, just like before. But then, it hits a special barium borate crystal. You can think of this thing as a kind of quantum photocopier. It takes that one photon and spits out two new lower-energy photons. And these aren't just any two photons. They're quantum twins, linked in a very deep and mysterious way.
This link is called quantum entanglement, and it's one of the weirdest and most powerful concepts in all of quantum theory. What it means is that these two twin photons now share a single existence. If you measure something about one of them, you instantly know the same thing about its twin, no matter how far apart they are. It's pretty spooky.
Now, in this experiment, we give these twins different names and different jobs. One is called the signal photon, and its twin is the idler photon. And from this moment on, their paths diverge.
The signal photon travels a short, direct path to our main detector screen, which we'll call D0. This is where we expect to see a pattern. But its twin, the idler photon, gets sent on a much longer, more complicated journey through a series of beam splitters and mirrors. The whole point of the idler's path is that depending on which detector it finally hits, we can figure out which slit its signal twin must have come from. In other words, the idler carries the which-way information.
And here is the absolute genius of this setup. Because the idler's path is so much longer, its measurement, the moment we either gain or erase its which-way information, happens after its signal twin has already arrived and made its mark on that main detector. The effect has supposedly already happened before we even decide on the cause.
So, the stage is set. The signal photon has landed. The idler photon is still in flight. What does that main screen actually show? Does the future reach back and change the past?
After thousands and thousands of these signal photons build up on the main screen, what's the result? Do we see a wave pattern, a particle pattern, or something else entirely?
Well, the result is maybe one of the most misunderstood parts of this entire experiment. When you look at the raw data on the main screen, D0, you see nothing, just a fuzzy blob, no interference pattern, no two distinct bands. At first glance, it just looks like a bunch of random noise.
So, let's just get this out of the way. The simple answer is no. The future does not affect the past. The pattern on the D0 screen is set in stone the moment that signal photon hits it. It never, ever changes, no matter what happens to the idler photon later. There is no retrocausality. So, where does the magic of the quantum eraser actually come from?
The erasure doesn't happen in real time on the screen. It happens later, in a computer. It's a process of data analysis, of correlating the information from all the signal photons with the information from their Idler twins. It's a sorting mechanism.
Here's how it works. After the experiment is done, scientists go back to the data. They say, okay, show me only the dots on the main D0 screen whose twin Idler photons ended up at detector D1. And when they filter for just that data, an interference pattern emerges from the noise. Then they say, now show me the dots whose twins hit detector D2. And a different interference pattern appears, perfectly out of phase with the first one. When you add these two hidden patterns back together, they cancel each other out, giving you that fuzzy blob you saw initially. See, the scientists aren't changing the past. They're just using the Idler's data as a key to sort the signal's data into its hidden components.
So, if the future isn't changing the past, what is actually going on here? The implications are, in some ways, even more profound.
The myth is that a future measurement somehow reaches back in time to change a past event. But the reality is much more subtle. It's about quantum correlation. Because the two photons are entangled, the information from the Idler photons measurement allows us to intelligently sort the seemingly random data from the signal photon, revealing the underlying order that was there all along.
So that delayed choice isn't a choice that affects the photon's journey. It's a choice the experimenter makes about how to analyze the data. The choice is simply which subset of the total reality you decide to look at. You're not changing history. You're just choosing which version of the story to read from the complete book of data.
And this brilliantly illustrates what John Wheeler himself concluded. A quantum event isn't a simple, isolated thing. Its reality is defined by the entire experimental context, from the moment the photon is created to the final measurement of all its entangled parts. The phenomenon is the whole story, not just the first chapter.
And this is the true mind-bending takeaway. The quantum eraser doesn't prove that we can rewrite history. It proves that, at the quantum level, history was never written in ink to begin with. The path of the photon wasn't a fixed, solid thing. Its past remained a haze of possibilities, only snapping into a definite story when the entire, system-wide measurement was complete. And that leaves us with a final, staggering thought. We tend to think of reality as a movie that plays forward, with the past being a fixed reel of film. But what if that's just a classical illusion? If the quantum past is only given definite form by its relationship to the present, what does that say about time, causality, and the very fabric of the universe we inhabit?